the traditional method is finding these tools by hash. Everybody's got these different archive tool, zips and unzips tools on their machines. Using hashes is silly, because it's really pointless, because what are you going to look for per se? So, and it also makes you always question what's inside the archive. All right,
hey guys, my name is Tomislav Peruchin. I'm the Chief Software Architect with the Reversing Labs. And before we continue, I'm just going to switch the slides, because I'm sure that everything we are meant to present till the end of the presentation is in here.
Yeah, move the microphone closer, or ask people can hear you.
So this is what we already talked about, and we're going to continue with the story about what we discovered and how. So if you look at the archive formats, usually you're talking about the most popular ones, and these are the ones: zip, rar, cap, 7-zip, and gzip. Now these are the files you will normally find on any operating system and any PC in the world. But if we look at them this way, you will most commonly find these first four on Windows and Unix for Gzip. But that doesn't mean that's going to be the case, because files are just binaries and they're not binded to the operating system in any form. But we selected to split them this way because their archive processors are commonly built for these platforms. Now, first format is the zip file format, and it is most common file format in use today. What's interesting about it is that it's over 20 years old. So it was invented or created in 1986 by Phil Katz for PKZip. Of course, the format itself is fully documented, and this is very important. The documentation for this file format is 32K line text file. So if you're implementing your own solution, you really have to go through all of that. And even the most popular archive processors, such as WinZip, haven't implemented all the features. So you see, you can create a file that's legal by documentation, but it really can't be opened by a standard tool that we use today. So, such as the WinZip, which is the most popular zip archival program, PowerZip, WinRAR, and 7-zip, of course, which is the open source version. Now, this format supports error recovery, multi-disk spanning, encryption, and SFX. It has multiple compression algorithms, but the default one is deflate. Now, the Rarefire file format is a very popular one. It was developed by Eugene Rochelle, and it is partially documented. It's a technical note you get with the program, and it doesn't really contain everything you need to know about the format, but it's a place to start. So its decompression is supported by WinRAR, of course, which is its native archive processor. You can download an SDK which works with the RAR archives, but it only gives you an option to decompress the archives. You cannot compress them. And these other programs, of course. Now this format, of course, supports error recovery, multi-disk spanning, encryption, and SFX. Those are the most common features we find in today's archive processors. Compression algorithm is a bit different, but it's based on LZ and PPMD, though it's proprietary, so that's why you need a license for it. Now, the cap file format is a very common installer format. It's very rarely used by users. It's created by Microsoft, and it's used as installer format for their platform. It is fully documented. It has a 20-page PDF file you can look at. It's a pretty detailed one. So the cap file format is, of course, supported by many software utilities, such as Microsoft Windows, who has included compressed folders, and it has support for both zip and cap files. What's interesting is that of all these tools, only Power Archiver can compress files into cap archives. And once you create a cap archive, you cannot add any more files to it, because that's how the specs work. And it supports multi-disk spanning, digital signing, and SFX. Uses 4 compression algorithms: LZX, deflate, quantum, and MSZip. 7-zip, as we talked, it's an open source format. It started in 2000, and it was developed by Igor Pavlov. It is fully documented. It has a series of text files you can look at and see how the format looks on disk. its native processor is 7-zip, of course. All the other tools also support 7-zip. It has multi-disk spanning, encryption, and SFX. For compression algorithm, it uses its own LZ variation called LZMA. Now, the Gzip file format is most commonly found in Unix. It was created in 1992, and it is documented just by a few pages in 96. Now, it is also supported by every known and most popular archive processor. Now, it only supports compressing single file. So if you want to compress more files, you have to bind them together with another program, usually it's star, and then compress the end result. It only uses the plate algorithm. Now, since we know all this about these formats, we wanted to know what does it all mean? It means that all files on the file system are basically just binaries. And if you look at any file, I mean doc, PowerPoint presentation, movie, or an archive, it's just a binary you can see with the hex editor and edit any bytes to your choosing. But to edit files successfully, you have to know the documentation for that particular format in order to modify the file correctly. So what are our goals when it comes to malforming files? From a steganography standpoint, we want to hide files or any messages from you. And we want to do that in a process which can be reversed. So once you've hidden something inside an archive, you must be able to retrieve it later. And from a vulnerability standpoint, we don't want to hide anything, but we want to break an archive processor. Now, this is really neat because multiple security vendors have developed their own archive processors. And since for Zip, we said the documentation is 32K lines long, you bet there are some things they looked over. Now, why does fuzzing doesn't apply to this scenario? Because we don't want to crash the program. We just want to break an archive processor so it just skips over a file and doesn't scan it in full. Now, how is it achieved? First and foremost, you have to know the documentation. Nothing can save you from it. You have to read the entire documentation and just think of certain features such as this is something nobody would implement, and just try that. And if that works with archive processors such as WinZip, you might want to try that with security tools. Now, documentation itself is not perfect. There are some things that are really unclear, and if you look at the Zip documentation, there are sentences that really don't make no sense. So you can use that to your advantage and think of the ways how anybody would implement that. You can use rarely used fields, as I said, that is basically knowing the documentation very well. And you can combine a couple of file formats together to create this sort of a weird file we will present later when we combined Zip64 format with the normal Zip format, and just try to mess with the format identification so not the proper algorithms are used to decompress the archive. And of course, there's try and error method. You can just try to change some bytes and see how that works or doesn't. Now, steganography is achieved by all of the above, and you can also inject more data into the archive. Now, there were some previous works in this area. There were some archive malformation tests that were published in 2004 by iDefense, and their implications are quite nicely put by ESET. I'm going to read this. It says, the vulnerability was caused by the fact that some archive decompression software, including WinZip, incorrectly handled compressed files with deliberately damaged file headers, thus in fact allowing creation of damaged archive files that would automatically be repaired on the victim's computer without notifying the user. And that's what this is really about. And this is what we focused our testing on. Now, the first thing we wanted to know is how fast and how accurately are we detecting formats. This is very important because this is the first step in processing any format. Second one is, if you get a file, you have to know if it's valid or not, and if it's corrupted, you have to know what amount of data you can recover from that. And of course, if our code was vulnerable to any of the known attacks or the future ones. And then steganography came into the picture, and we wanted to know the following. We wanted to know, is there interesting data between all these files and archives? And even so, if there is this data, can we corrupt it? Can this data have a self-destruct button? Now, here's what we found in our tests. from Steganography.